Hi everyone, in this video we'll study Quicksort and Randomized Quicksort. Now both Quicksort and Randomized Quicksort are sorting algorithms. So what they do is they take as input a sequence of numbers a1 to an, there are n numbers, and the output is a sorted sequence of these input numbers. Now the algorithm uses the divide and conquer approach. So Quicksort is a divide and conquer algorithm. So here we have the code for Quicksort, and what Quicksort does is it first divides the array A. So A is your array here. And what Quicksort will do is divide A into two subarrays. And these subarrays could possibly be empty, but our hope is they'll not be empty most of the time. So two arrays. The first array starts from AP and ends at AQ minus 1. And the second array starts from AQ plus 1 all the way up to AR. Now, notice that AQ is not part of both these arrays. Now, in line 2, we have the partition functions which gives us this Q. So, we are partitioning the subarray into two subarrays such that every element in a p to q minus 1 is less or equal to AQ. So all elements in A p to q minus 1 are less or equal to AQ, and every element in AQ plus 1 to R, this array, is greater than AQ. That is basically what we want to achieve. Okay, that's what this partition function here does as well. It returns as index Q and partitions it. Okay, so this is essentially the divide step. Okay, so the divide step is the most important step in the Quicksort algorithm. The conquer step is simple enough. So in the conquer step, what we will do is recursively call Quicksort. So recursively call Quicksort. That's what you do in the conquer step. And the combine is actually very simple. There is nothing much to do in combine because the array will naturally be sorted. So there's nothing actually to do in combine. So all the work is going to be done in the divide step and the conquer step, which is basically to recursively call this algorithm. So you must have noticed and you must have realized by now that the partition A function is the key part of this divide and conquer algorithm. So next we will study the partition function. So for your benefit, I've already written the partition function here. So we will go ahead and study this partition function and how it works using an example. Okay. So first, let's consider the array A. Okay, well, we'll consider an array A and consider step A here, which has elements 2, 8, 7, 1, 3, 5, 6, 4. Okay, so at this point, P is here and R is here. That's where. Okay. Now, initially, if you look at line 2, I is P minus 1. So I is actually one step behind. This is where I is pointing to. And in the very first step, j will be equal to p right here. So j will be equal to where p is pointing. So j will also be here. Okay. If you look at line 1, which you just skipped and move ahead, AR will be equal to x, which is 4, and x will be equal to 4. Okay, so that's how this algorithm starts. Okay, now let's look at the next step of this algorithm. Now, what it does is you're going to compare the elements of this array. So you're going to go all the way from p to r minus 1, which is r minus 1 will be somewhere till here, right? So the for loop is going to iterate from p to r minus 1. I'm just going to erase this arrow here. So that's where how this for loop. And every time you're going to compare in line 4, aj, then element, with x. Now, so all elements are going to be compared with x, and essentially we are going to find the right position for x in this array. That's what the partition function is going to do. Now, what happens here is you're first going, if aj is less than equal to x, which it is. aj is less than equal to x because aj is 2, x is 4, so that is less. So what you're going to do is you are going to increment I first. So first I is going to be incremented. Okay. So R will be here, P will be here. So P and I will both be here at this point. Then you're going to exchange AI with AJ. At this point, AI and AJ are the same, so they will be exchanged and essentially will remain in the same location. Okay. And now what is going to happen is I'm just going to fill the list of this array. So note that AI and AJ were the same thing. They both were 1. I and J were both pointing to index 1. So the exchange did not change anything in this. I'm just also going to use a separate color here. And we'll see why that is the case. So after this, when we come back to line 4, J will have moved here. That's where J would be. Okay. So now, once again, line 4 will execute. At this point, AJ and AX are going to be compared, and AJ is greater than X. So it's not going to do anything, and just J is going to move forward. So we'll have the same array. So you will have 2, 8, 7, 1, 3, 5, 6, and 4. Everything will all remain the same, just that J would have moved forward. I'm just going to use this blue line here, and we'll talk about what this blue line is going to do. Essentially, it's going to separate some elements out. Now, you're going to compare, go back to line 3, then come to line 4, again the comparison, 7 is greater than 4, so J is just going to increment. So you're now going to have this array as 2, 8, 7, 1, 3, 5, 6, 4. J will now be here. P and I both will be here. Okay. So this is how it's been progressing. Now you're going to compare 1 with 4 in line 4. Now what is going to happen is you're going to increment I. So let's do that. So first, 1, 2, 3, 4. Okay, so we'll have 4 here. I will go here. Because line 5 will execute, I will actually move ahead. P will be here, R will be here. Now, you're going to exchange AI with AJ. So AI at this point is 8, and because I got incremented, and J is 1. So you're going to exchange those two. So we're going to get 1 here, and we are going to have 7 here and 8 here. I'm just going to use blue color. So you see 8 is going to be copied over here. That's what is going to happen. So it will be 7 and 8 because we're going to exchange AI and AJ. Okay. So that's how this is going to look. I'm going to draw this blue line around these 2 points here. Okay, just to make everything clear. So you can now see a pattern emerging. What we're trying to do between those 2 blue lines is we want to keep all these elements that are greater than 4. Now this 4, AR or X, that's called the pivot element. So 4 is going to be placed in its correct location. And now you can see this pattern emerging. So let's now do next step. So after this, J will have moved here. Now J again is AJ, which is 3 is less than 4. So once again, you're going to increment I first. So we are going to have P here, R here. I will be here. So I will essentially be at 7th position, and you're going to exchange 3 and 7. Okay, so you're going to have 3 come over here, and then what we are going to have is 8 here and 7 here. This is what is going to happen. Then we are going to have J be at this location. Now, once again, you're going to go to line 3 and then line 4. At line 4, you will see that AJ, which is 5, is greater than 4. So nothing is going to happen. And we're going to show this by this. So here essentially just J is going to get incremented. Okay, that's essentially what happens. So have these numbers like this, and we will have P here, I here, and J here, or P here. So this is essentially what is happening here. Now you're going to compare 6 with 4. 6 is greater than 4. So once again, J is going to get incremented. That's all that is going to happen. So J will get incremented. Let me just erase this. It's in blue. So you will have 2, 1, 3, and 4 here. All the other colors you will draw in blue. 8, 7, 5, 6. Okay, this is how it will look like. And P will be here, I will be here, R will be here, and J would have moved here. Now at this point, J is equal to R. So when you come to J equals R here, it will essentially jump out of this for loop. Just a moment, sorry about that. So J equals R, so it'll get out of this for loop here. Okay, so it'll come to line 7. And in line 7, you're going to exchange AI plus 1 with AR. So you're going to exchange this with this. That is what is going to happen. Okay. So we are going to keep 4 in its correct position. So now you're going to have the array look like this. 2, 1, 3. I'm going to now use a separate color to place 4. Then you will have 8, sorry, it will be 7 first, 5, 6, and 8 here. So 4 has been placed in its correct position. So P will be here, I will be here, and R will be here. So what we have done is we have, at this point, placed 4 in the correct position of this array. So if we go to this partition algorithm, what we're doing is we're trying to find where to place the pivot element, or 4, here in this array. Okay, so now if we go back to Quicksort, it calls this partition, so Q, it gives this index Q, and you continuously recursively call Quicksort. So essentially every time partition is called, the pivot element will be placed in its correct position as is shown here. Okay, so this is essentially how Quicksort works. So now let us try to understand the runtime of Quicksort. Okay, so let's do runtime analysis. Now, if you look at the worst case, right? So because it's a recursive algorithm, Tn is when you have if you consider the entire input of n numbers. Now it could so happen that every time you get an array of no elements and the other array of n-1 elements. Okay, that can happen. So you can split, when you split the array, you can have one array containing n-1 and the other array containing no elements at all. And then the partition takes theta of n time. So you will have seen that in this partition function, right, you're just going through lines 3 and 6 where you just go through the entire array. So if it's n-1, you're going to take theta of n. When will this kind of like to happen? When array is sorted in ascending or descending order. So when you have the input array as being sorted itself, then this is going to happen in Quicksort. And this can be solved easily with substitution. And if you do that, like if you keep substituting it, you will find that the runtime is theta of n squared. So in the worst case, the runtime of Quicksort is theta of n squared. It happens when you divide the two subarrays and they are unbalanced. That is, one side has all the elements and the other array is empty. That's why I said in the beginning that we don't want that to happen, because if that happens, you will get the runtime to be theta of n squared in the worst case. Now, on average or in practice, what happens is you will not get such an uneven split all the time. So on average, Quicksort takes theta of n log n. Okay, that's just the average case. It happens when you have something called balanced partitioning. Okay, so in the worst case, you will get theta of n squared. But if you have balanced partitioning, you can get theta of n log n. Okay, so now that we've studied Quicksort, let's just quickly study randomized Quicksort. Now, randomized Quicksort is actually very, very simple. Okay, it is essentially the same Quicksort algorithm with a very minor difference. So I'm just going to write the algorithm first. So in randomized Quicksort, what happens is we'll have a randomized partition. Okay, so we will use randomization. So we saw that if the array is sorted in ascending or descending order, Quicksort gives theta of n squared as the worst case runtime. Now, if there is a pattern in the array, we want to disrupt that pattern. That's what is causing this worst case runtime. So we want to disrupt it. So to do that, what we do is, in randomized Quicksort, we randomly choose an index between P and R. Okay? Then we exchange AR with AI. So we just exchange the pivot element so that if you have a sorted array, that pattern gets disrupted. And after you've exchanged it, you're just going to call the partition function that we studied. So you're just going to call partition. So you're just going to exchange the pivot element, and then you're going to call partition like we did earlier. So this is essentially the randomized partition. So there's no change in the algorithm per se. You're just not going to consider the last element of your pivot. You're just going to pick any element in this array as a pivot, exchange it with the last element, and then run your quicksort again. Now, how will the randomized quicksort algorithm look like? So randomized quicksort will look exactly same as quicksort. You're not going to do much here. It'll have the same look and feel. So first, you're going to check if p is less than r. That's the case. You're going to get the index q by calling randomized quicksort instead of calling your general quicksort algorithm. And then you are going to call randomized quicksort twice. So you're just going to call randomized quicksort recursively. So the algorithm is exactly the same. Okay. Now, before I complete, I just want to talk a little bit about the runtime of randomized quicksort. So in practice, randomized quicksort breaks up these patterns that can exist if the array is sorted in one direction or the other. So that is essentially what randomized quicksort does. But randomization cannot overcome the worst case. It can still happen that you can get an array such that one side has all the elements, one of the subarrays, and the other subarray does not have any. And this can happen each time. Even if you use randomization, it's possible. You're breaking up patterns, so in practice, randomized quicksort gives better performance than quicksort, but the worst case is still theta of n square. So worst case runtime is still theta of n square. But in practice, it performs better than quicksort. I hope in this video you understood quicksort and randomized quicksort, and you saw how divide and conquer can be used to solve the sorting algorithm for sorting, and how it is a useful algorithmic paradigm. I hope you enjoyed this video. If you like this video, please subscribe to my channel. Thank you.